Thank you. So I was asked to talk about the TA, or at least US array, and I think I was asked also to basically propagandize about the TA and its tremendous quality. So I will be focusing on some examples of work that demonstrates the high quality of TA, and I will I will be pretty seismological and not really talking much about the interpretation, since I'm focusing on the quality of the seismic data. So in general, I believe I have a very strong bias towards thinking that quality is the greater challenge. And I think quality, you can talk about quality of the data. You can also talk about the quality of the instrumentation or the project or the science, of course. And I think that the TA, basically, how can you evaluate whether the quality was good or not? Well, if you've done something, written a paper, or gone through a deployment, and you say, right after you finish, you say, I wish I had done it slightly differently. I wish I had done it better. Then that suggests that maybe you hadn't focused enough on the quality. So hopefully, well, my sense is that the TA has been completed in the lower 48, showing that it is a quality project. I thought I would just look back a little bit to where it was. The idea of having a roving array is, of course, goes back longer than 1998, but 1998 was really the year when the IRIS community gathered around this idea, and there was a workshop in 1998 that resulted in various documents being written, and one of them was this vision of what the TA might look like, or what US array might look like. And in 1998, there was the concept of a roving array, shown there in the 100 red dots, and that the idea at this point was that those red dots would move around after deployments of 6 months or so, move to a new place, and then with 20 or such deployments, you would cover the surface of the lower 48. It didn't happen easily that we agreed on this as a concept. In particular, the regular grid was seen as something stupid, since really we know what we are looking for, we know what those geological targets should be. And there was a discussion in the community, and then there was, if not a consensus, at least an agreement that no, TA is good as long as we have a flexible array as well to look at the targeted investigations. But I should emphasize that we really didn't know exactly what we were going to find with this array. Things moved quickly initially. In 1998, we had this not as ambitious of a plan as what was eventually enacted. But in 1999, we basically had the full idea of 400 stations with 1 or potentially 2-year deployments going out fixed. And then, of course, nothing happened for several years, as we heard earlier today. And we really didn't start deploying the TA until 2005, 2006, where we started with using existing instrumentation largely, and then slowly augmenting it with the transportable array. So one of the remarkable things is that we were able to convince people to do this without knowing that one of the most exciting things that the TA has produced, we didn't even know that that was going to be possible, and I'm talking about the noise tomography. That whole idea of using noise in this way to image the crust and shallow mantle, technique wasn't there. There was, of course, early theoretical work that showed that you could use noise in this way, but it was not really until the early 2000s that Campillo and others showed that you could use this for tomography. And I think one of the most exciting results that have come out of this is the noise tomography. And it's remarkable that we were able to convince ourselves that this was going to be useful without understanding that we were going to be able to map the shallow continent. So I'm going to show you my version of this. Of course, Ritzwaller and his students and postdoc have been pioneers in this field, but I'm going to show my own results. And here is just what the maps looked like back in 2000, using data from the first month of 2006 up until that point. And what we're looking at is Rayleigh waves at 6 seconds. And here we see the continent being mapped out by just using the initial or the subsequent deployments of TA across the continent. And as the last stations went into Maine in September, October of last year, we now have the full map for the lower 48. So, of course, what we see here are remarkable variations, minus 50% or more, up to plus 20 in this map. And we're seeing here, of course, at 6 seconds, the very strong indications of the sedimentary structure, shallow sedimentary structure. And you can pick out your own favorite sedimentary basins here. And, of course, on the East Coast, we also see very intriguing structures associated with the various orogenies. And we can do it with Rayleigh waves. We can do it with love waves. And with love waves, we, of course, see even more remarkable variations. And in particular, what stands out here is the extremely low velocities in the along the Gulf Coast, minus 60%. I'll show you a little bit later what that translates into absolute velocities. So this is, I think, a remarkable success. It turns out that these results are very robust. Robust in the sense that you can use different approaches and you can use different data. And here I'm just showing that the first map, the top map shows what you get if you use the vertical component of noise and you correlate it. And the bottom map shows what you get if you use the radial component of noise and you correlate it. And I think these are essentially indistinguishable. And robustness, of course, is good, but it's also bad, because it turns out that not only is it robust if you use different data, but different researchers get the same result. And for tomography, that is usually very bad. So because what are we arguing about then? And in fact, I think maybe that not that many people are actually pursuing this mapping of the whole continent, because it's already been done. But we should actually use this in the sense of using it for science. The next step, what do we take, what do we use these maps for? Just another example of how robust these results are. This top one is the standard two-station correlation methods that we have, and those who are familiar with this, you can also do correlations of the correlation functions. And you can see here, which is a technique to remove some of the bias that you get from the noise sources. And you can see that, again, the agreement between these two maps is remarkable, suggesting that the results are robust. So I'm not, as I said, this is really going to be mostly about the wiggles, so I'm not going to go into the interpretation, but that is obviously the next step. So I just want to illustrate here with two locations and two predictions of what we should see. So the stars indicate two locations, one in Minnesota, one in Mississippi. The dots on the right-hand side is the dispersion diagram from 40 seconds to 5 seconds, which is the range over which I have done noise tomography. The dots indicate the observations, the measurements, and the solid lines are the predicted dispersion curves. And these are predicted dispersion curves from a crustal model, in this case it's Crust 2.0, and a mantle model. And it's the Nettles-Jaworski mantle model. So the mantle is not that important except at the longest periods, but the crust obviously is. And what you see here is that in Minnesota, we have a pretty good handle on this already in Crust 2.0, whereas in Mississippi, where we are observing Rayleigh wave and love wave phase velocities around 1.5 kilometers per second, the current models are just not able to predict such slow velocities. And even with better, maybe Crust 1.0 will get us a little bit closer. But the thing that is problematic here, I think, is that we have shear wave velocities at great depth in the sedimentary pile that are much lower than we would predict from standard conversions from P-wave velocities, which are, of course, better known. Okay, I'm going to move on to some specific things about quality. And I want to address two things specifically for the TA, sensor orientation and sensor calibration. So sensor orientation is just how well do we know whether the horizontal components are oriented in the direction that we say they are oriented in. So we have a desired orientation and a true orientation. And we can determine that, of course, by measuring it in the field, and that's done when the station is installed. But we can also try to tease it out directly from observations. And that's what we have done. So we are using surface waves, and as you all know, Rayleigh waves should only show up on the longitudinal and vertical component, and the love waves only on the transverse component. So if they don't, if the instrument is not oriented the way you think, then as is illustrated in these seismograms here, you end up having love waves on the radial component and Rayleigh waves on the transverse component. A result that could of course, be very interesting, also resulting from anisotropy or multipathing and so on, but frequently the result of the instrument not being properly known, the orientation of the instrument. So very early on in the TA, I started trying to determine these orientations of the instruments directly from love and Rayleigh waves. And using the data that was available for 2006 and 2007, we found that a lot of the TA was misoriented. More than 5% of the instruments were more than 10 degrees off, and more than 10% of the instruments were more than 5 degrees off. And Bob Busby took this very seriously, wanting to have a quality array, and implemented new techniques to measure the orientation of the instruments. And together with Bob's feet there, you see this instrument, the Octane, very expensive French instrument that tells you the orientation of things. And it can be applied then to the STS-2 in this case, and you can get a true measure within a degree or so, I believe, of what the instrument orientation is. And on the right-hand side in the slide, you see the correlation between the seismically determined orientations and the measured orientations in the field using this instrument. And subsequent to this, I believe the TA instruments were oriented both at deployment and when they were taken out of the ground to get very good and accurate orientations of the sensors. So following this, the TA has become a remarkably well-oriented network. And this just shows the distribution of polarization anomalies for each station across the array. And you can see that the half-width of this peak is around 3 degrees or so. And in fact, if we show it on the map, what is shown here is the anomaly. Green means that the orientation of the sensor is within 2 degrees of, based on the seismological. I mean, we don't actually know the true orientation, but based on the seismological analysis, it's within 2 degrees of what it's supposed to be. And then the yellow and the light blue span the range of +5 to -5. And you can see that most stations actually fall within this range. You can also see that there are anomalies. The other colors, not those that I just mentioned, indicate instruments that are not as well oriented. And the ones that are squares are actually not TA stations. Those are permanent stations. So you can see that actually many of the misoriented instruments belong to permanent observatories. The bottom line of all of this is that the TA is what I think is the best oriented set of instruments in a substantial array, and it's borne out by these statistics. You have to realize that we still don't know true ground truth, but these are measurements. This is the seismically determined versus the metadata orientations. And as you can see here, of the epochs of the meanings individual instruments that have been deployed, 92.2% of the TA instruments are within 3 degrees of what they claim to be, and 98.9% are within 6 degrees. And as you can see, at least in the left column, there's no other network that achieves this, not the global networks either, which I have included at the bottom. Of course, if you go to the middle column there, you see that the Berkeley network, all of the stations are oriented according to the seismic data within 6 degrees. So I think that this is one of the reasons why the TA data can be used with confidence for doing certain analyses, not necessarily polarization analyses, but even looking at SKS or looking at receiver functions to be confident that your instrument is well oriented makes it much easier to use the data, which is why high quality data get reused over and over again. So we have not used polarization of the wave field to do anything, but we have looked at the geometry of wavefronts. So then moving on to a different topic here. Here is a map showing wavefronts, which of course you can map out by just continuous face or same face of a wave field measured across the TA. So what you see on the left there is the yellow are the wavefronts of something traversing from left to right. And we can determine the orientation of that wavefront by using mini-arrays, meaning taking a small sample of stations and calculating what the arrival angle is within that mini-array. And when we do that, we can map out arrival angle anomalies of surface waves. This is Rayleigh waves at 50 seconds now, I should have said. So on the left-hand side, you see the representation of the wavefronts. On the right-hand side, color-coded at each station, is the center of a mini-array where we have an arrival angle anomaly. So the red ones are clockwise, blue ones are counterclockwise anomalies. And you can see these streaks, which represent perturbations in the wavefronts as they traverse the array. And the interesting thing with this is that these patterns are reproducible. So here are two events in the same location, and measuring the same kind of mini-array measurements of arrival angle anomaly, we see the same patterns. So that's good. It shows that those things are robust. But also with the roving characteristic of the TA, it means that you can combine different time sequences and get larger maps of arrival angle anomalies. So you can actually illustrate the full deformation of the wave field as it traverses the United States. And this is just showing some results from western US, showing these arrival angle anomalies from events coming from Easter Island, composite of many different events, and same thing from Loyalty Island. And of course, this could be extended across the full array. We haven't done that yet, but it could be. So, okay, that's interesting. All of that information, of course, exists in the phase data to begin with, but the characteristics of these anomalies tells us something about the scale of heterogeneity and the scale and about wave propagation and wavefront healing. So I think one of the possible ways that a data set like this could become very useful is in diagnostics. So what I mean by that is that on the left-hand side here we have the observed pattern from Easter Island events observed across the array. On the right-hand image is a synthetic. It's a full synthetic, meaning that we've generated seismic waveforms using SpecFEM for a particular model. In this case, it's a global model with the crust 2.0 on top. And then we've made the equivalent measurements on the synthetic waveforms. So it's basically simulating the whole thing from the earthquake to the waves being observed to the measurement technique. And you can then identify patterns that fit and patterns that don't fit. And clearly, this model, which admittedly was not a regional model, but you can see that several of the patterns, the red to blue, is matched, but the details, which obviously reflect smaller scale structures in the Earth, are not matched. But as more models of 3D structure become available, this will be a possible diagnostic tool for figuring out which model is actually correct. Moving on to a new topic, which is the amplitude calibration of the TA. So the symptoms of a seismometer with the wrong gain is obviously that the observation doesn't fit the calculation. Here is a TA example of a gain at one station, vertical component being off by a factor of 2, which is something that can happen if your differential gain is, you set it wrong or the instrument is not actually recording differential signals. So factor of 2 is fixable, and of course it's also a clean number, factor of 2. You can fix it in the metadata. So how good is the TA in terms of amplitude calibration? As many of you know, we typically look at phase for most tomographic problems because phase is very robust, whereas amplitudes are affected by a lot of things that we don't know about, including station calibration. So an initial test that we did was to basically just calculate scaling factors for all synthetic seismograms that we generate in the CMT project, and just divide that, or calculate for each station for every earthquake what is the scaling factor, and not ignoring all the wave propagation effects and so on, just getting a raw number and averaging it over all observed seismic events. And we get a large range. You can't see it, but it's plus minus 30% here in terms of the scaling factor. And so that could either mean that stations are very poorly calibrated or there's stuff here that we don't understand, and it's actually the latter. Here's a map of those scaling factors. And the interesting thing here is that each of these numbers is a number that is only related to a particular station, right? There's no smoothing involved here. So the coherent patterns of these, where the color scale, I should tell you, green is between plus minus 5% scaling, yellow is 5 to 10, and light blue is also 5 to 10. And you can see the most extreme ones are a factor of 40% or so. But the important thing is that blues tend to be grouped with blues, which shows that adjacent stations actually have very similar scaling factors. There's a regional pattern here, which I think has nothing to do with Earth structure or little to do with Earth structure, might have to do with global seismicity distribution and things like that. At least it's convolved. The two things are convolved. But the spatial correlation tells us that at least the array itself is well calibrated. Now, we've done, Celia Eddy has a poster about this, but we have also looked at this in more detail, looking at amplitudes recorded on adjacent stations, where you can remove a lot of the propagation effects, the earthquake radiation patterns, and so on, and just look at the relative amplitude on the two stations. So you measure Rayleigh wave amplitudes for many sources at all stations. You form amplitude ratios for nearby stations. You average those ratios over a lot of events, and then you link together all of those ratios to get a map that tells you about the whole array. So here are observed, and what does that give you? It should give you the amplitude factor that is related only to the structure below that station. We should have removed everything related to the earthquake. We should have removed everything related to the propagation and focusing and things like that. And the thing that we hope remains is something that relates only to what the Rayleigh wave is doing at that place, which is determined by the radial elastic structure. So here we see what the result is. Observed local Rayleigh wave amplification factors. These are, we believe, related directly to local elastic structure. And again, here you can see a few outliers. Those are stations that indeed do not have the correct gain. But for the most part, you see these very coherent patterns indicating that the differences in calibration of adjacent stations must be really, really small. And the patterns, of course, are very interesting. At the top is a long period, 125 seconds, averaging elastic structure down to at least 200 kilometers. And in the bottom panel, you see the 50-second maps showing regionally consistent patterns that we believe must be related to elastic structure. And in fact, if we compare the observed amplitude factors with those that we would predict from a tomographic model of the United States, we get very good agreement, I would say anyway. So these are Rayleigh wave local amplification. Again, at the top is the observed measurement. And at the bottom is that it's been predicted using a mantle model. It's very important to get a mantle model in there because the east-west variability in the shallow mantle is very large beneath the USA. But then, of course, crustal structure has very large impact on amplitudes as well. And you can see large-scale correlation, good correlation. And, of course, the important thing is that this data set is now available to refine that elastic structure in future models. So a specific quality result that has come out of this study is that there's no smoothing involved here, right? So these numbers are only based on that individual station, which tells us that the scatter being so small tells us that the individual stations must be very well calibrated in amplitude. And in fact, if we look at the spatial coherence in the sense of how big is the difference between the scaling factor between two adjacent stations at different distances. You can see that as we go from right to left in this graph, closer and closer pairs, we see that the scaling factors come down to being different only by a factor of 0.0 to 0.03. So I believe our conclusion from this is that the average calibration of the US array TA is of the order of 2%. And if you have not worked, have had the reason to work with amplitudes, for example, if you have not tried to do Q work, you may not be aware of the fact that this is a remarkable number, that pretty much any network that you go out and look at, having factors of 10% in gain away from what is given in the metadata is not an unusual occurrence. So again, the high quality of the TA in its amplitude calibration makes it much easier to, with good without worrying too much about the instrument going out and actually trying to interpret the amplitude anomalies that you see in terms of interesting geophysical things as opposed to relatively uninteresting instrument things. So from the strictly quality of the instrument kind of viewpoint, conclusion with respect to that, I believe from our empirical studies, we find that the TA is oriented with perhaps within 2 degrees, 1 sigma deviations, which is remarkable, and of course the even distribution and the large footprint of the TA makes this data set a unique opportunity, provides a unique opportunity for investigating the polarization of the wave field, in addition to, of course, simplifying a lot of other seismic analyses. The potentially even more impressive thing is this, that the US TAs are so uniformly calibrated, which again makes it much easier to interpret amplitude variations that you see in terms of interesting geophysical signals. So moving forward, I think that IRIS, whatever its next big thing is going to be, or whether it's improving the core or whatever, I think that one should not forget that quality is really the thing that makes data sets valuable to yourself and to the next person who might want to use those data. However, I also wanted to end with this figure. So also, I think we should not forget, even though I've had a lot of fun working with TA and the TA data, and hopefully my students have too, it is really a seismological kind of endeavor trying to tease out these signals from a completely new type of facility, the TA. But, of course, we had here the Earthscope science plan, unlocking the secrets of North American continent. So I can't really claim that these amplitude factors are a secret of the North American continent. They might be a clue to a secret, but they really are not the end product, right? So the greater challenge, I think, even though the challenge, of course, of having impressive facilities is great enough, perhaps, for this community, but the greater challenge is probably to make sustained use of these data to look at these multidisciplinary and cross-cutting problems and actually come up with a plan to solve some of these questions that we have identified in a number of different documents. Thank you.